Okay, maybe I can start.
Yeah. And let me first introduce you
Okay.
and our speakers. So first of all, thank you all guys to join today's SPARKS seminar. And today we are glad to having introduced two experts in their fields. So our first speaker is Hongbo here. Hongbo is an AI Edge postdoc right now. He previously received a bachelor's degree from Jiao Tong University, and then he finished his PhD degree back in 2024 in Singapore University of Technology and Design. And his research interests are learning theory, network AI, and game theory. And today he's going to bring us his recent work on mixture of transformers. So yeah, go ahead.
Okay, yeah. Thank you for the introduction, Richard. Let me share my screen. Can you see my screen? Okay. Yeah. Hi, everyone. Thank you for joining today. I'm Hongbo, a postdoc scholar at the AI Institute, and today I will present one of our recent works, so mixture of transformers learn faster, a theoretical study on classification problems. And the collaborator includes Qinghang Wu, a PhD student in AIH, and Prof. Sun Lin, Prof. Yingbin Liang, and Prof. Nesraf. And during my presentation, please feel free to interrupt if you have questions, and I look forward to your feedback. Here are the motivations. So, yeah, transformers are very popular in the current machine learning problems, but it currently faces scalability challenges and significant computational costs when applied to diverse or large-scale tasks, particularly when these tasks involve conflicting or heterogeneous feature patterns. This is because in transformer, it usually employ a simple FFNs. So for each layer, FFN there is only one FFN, so it faces scalability challenges. And to solve this problem, recent work has employed a mixture of expert model, so which expand a single FFN to multiple FFNs, such that each FFN only need to handle a class of tasks. So it can greatly improve the efficiency of transformers, but current work mainly focus on empirical study, and there is a lack of unified theoretical explanation, and especially when both FFN and attention layers are allowed to specialize. So we aim to bridge this gap. And in the existing literature, is mainly introduced in the FFN layers, but leaving the self-attention shared across all experts. So they may have multiple attention heads in a transformer, but they are still shared across all experts. They do not have their own specialization. So it also limits the performance of the transformer. And recent works have proposed incorporating mixture of attention mechanisms into experts architecture, and it has demonstrated improved empirical performance, but these efforts are entirely empirical, and no existing theory explains how attention and FFN layer specialization interact. And we want to analyze the training dynamics of the mixture of attention and the mixture of experts in FFN. So we consider a full transformer specialization model, so named as a mixture of transformer model. So we view a whole block of transformer as an expert. So, and we propose this mixture of transformer model as a test bed, a theoretical test bed. And we conducted the first theoretical analysis with benefit characterization, and we provide theoretical guarantees on the convergence of MOT architecture to the optimum under our three-stage training process. And meanwhile, our analysis shows that MOT significantly shortens the convergence time from an order of epsilon power minus 1 under a single standard transformer to the log epsilon power minus 1. We proved that MOT greatly accelerated the convergence. And finally, we conducted extensive real data experiments to validate our theoretical findings. Okay, let me start introducing our data model and the system structure. We consider an N-mixture classification problem trained on over K independent data samples. So here, the N-mixture means for each data sample, it may contain multiple class of signals. For example, in image classification problems, we may want to identify a dog in an image, but there are some other noise labels, like there may be a cat in an image. So it also contains other signals. So it is a mixture classification problem. So we want to identify dogs among cats. So that's a difficult problem. And we use C and V to denote the set of class signals and classification signals respectively. We assume, so for use of analysis, we assume Cn and Vn are orthogonal to each other. So this is just for use of analysis. And in our experiments, we have shown that this assumption is not necessary in practice. And we let L denote the number of tokens per sample. So here is the definition of our data model generating process. So first, we generate a true label Y. So from +1 or -1 as the true label of a data point. And we generate another noise label epsilon. And then we generate a class signal Cn from the set of C. So it serves as so it determines the class of this data point, and we randomly sample a position to make it Cn, and we sample another position L1 to set it to be Y times Vn. So Vn is the corresponding classification signal, and Y determines the true label of this data point. And we sample another position to set it to be Vn prime, which serves as the noise label. So the transformer had to identify Vn to get the correct label Y for the correct prediction. And for the other L-3 tokens, we set them to be Gaussian noise vectors. And they has no effect on the label prediction. This data model is actually very general in practice. For example, in image classification problems, we can transform an image into a matrix, and some vectors serve as features like the classification signals, and some other vectors are just noise, so they have no effect on the label prediction. And like what I said before, so in an image, it may contain some features of other classes. For example, when we want to identify a dog in an image, the image may contain a head of a cat or tail of a cat, so as the noise label. So it will add extra difficulty for this problem. So that's the generating process for our data model. And here is the illustration of the MOT model, so as shown in figure A. So we use a whole block of transformers as an expert. So it includes a layer of attention and a layer of FFN. And we introduce gating network and router to route the data set to different transformers. And we want to analyze the training dynamic of this MOT model. We also want to compare it with the benchmarks to demonstrate its benefit. So we consider two popular benchmarks. The first is standard single transformers with multiple attention heads. Different from this structure, the multi-head transformer without gating have to update all the attention heads simultaneously. So they will concatenate the output of all these heads as the output of the attention layer. So this is the single transformer structure. And for another benchmark, it is widely used in the existing theoretical literature about MOE. And they don't consider attention, but only FFN. They specify the FFN into MFFNs, and they similarly use the gating network and router to decide the FFN. And so we will compare the performance of MOT with these two benchmarks later. And for the details of the MOT structure, so we model the gating network to be linear with the parameter matrix um, with linear parameter matrix theta. So theta contains the m vectors. So each vector corresponds to a transformer. So there are m transformers, and after inputting x, y, the gating network generates the linear output hi for each transformer I. So this is a linear combination. So hi corresponds to the gate output of transformer I. And we summarize the m values into a vector h for to denote the gating outputs for all transformers. So after deriving the h vector, the router needs to select an expert to route the data to this transformer. Here we adopt a top one routing strategy. So this is a widely used routing strategy. So we only select the expert with the maximum gate output because the router believes that the transformer with the maximum gate output is the best for the current data point. So it selects the expert M with the maximum gate output HM. And here R is an independent perturbation. So it will encourage the exploration in the early training stage, but after convergence, it will not affect the final decision. So in this example, the router selects transformer 2 and route the XY to this transformer. Then the transformer 2 generates the prediction result, and it will generate a training loss here. So the training loss will be used to update the gating network parameter theta by gradient descent. So if the loss is very large, it means the router selects the wrong transformer. So the theta will be updated. Then in the next round, when the same data point arrives, the router may switch to another transformer to see whether it is better. So this is the exploration stage. The router will explore transformers for any data points until find the best transformers. If the loss is very small, it means transformer 2 is very good for this data point xy. So by gradient descent update, the theta is just slightly updated. So when in the next round, if the same data point arrives, the router may still selects transformer 2 for training this data point. So this can achieve a very small training loss for this MOT system. And so here the router also calculates the softmax gate outputs. Because each eye has different scale. So some HI may be very large, some may be very small, and we need to transform them into a normalized value. So pi I is the probability that the router selects expert I. So we will use this pi I for updating the gating network parameters later. So I will introduce the update process later. So here is the output process of the transformer. Because we just employ a single attention layer. So this is the attention output. This is standard formulation for the single layer attention mechanism. This is the key matrix, and this is the query, and this is the value. So this softmax actually serves as a filter, and it will generate attention scores between 0 and 1. So if so XA will finally output values that has a maximum or has a very large attention scores in the attention mechanism. So after outputting XA, the FFN will compute its prediction result. So that it has its own linear parameter W to calculate the prediction. And so this is the final output of the MOT system. But this is looks very complicated because there are four trainable matrices. So we want to simplify it. So we combine WK and WQ matrix into a WKQ matrix, and we combine WV and this lower W into this upper W matrix. And this will not affect the final result, but just simplify the output. So we only need to focus on these two matrix training. So for the gating network update, so for the gating network update, we define the following empirical router loss function. So this L is the logistic loss, which is a convex function. So we use a convex loss here, and Y is the true label of the point K, and F is the output. So because Y is either positive one or minus one, so only when Y and F are both negative or both positive, the loss will be very small. So this is our training objective. Here we introduce pi m. So this is the softmax gate output here. So it is the probability that the router selects transformer I. So if the loss is very small, so if this value is positive, then only if pi is larger. So pi is larger, then the loss is smaller. So if we introduce pi here, it will drive the router to focus on a single transformer for each data point. So it will accelerate the transformer to gain its own specialization, and also it will accelerate the router to converge. So that's the function of pi here. And then we use the gradient descent to update theta as follows. Where for the transformers, it is a bit different because it has two matrices to be updated. Initially, we assume the two matrices of any transformer I are generated by a Gaussian distribution, and we need to train it by minimizing this training loss. So this loss is a bit different from the gating network parameter. A bit different from the empirical router loss because it doesn't contain this pi. Because for each transformer, it doesn't it is not affected by the routing strategy. So it only focuses on the output F. So we remove pi here for the training the transformers, but the two loss will converge at the same time. Because this is a two-layer transformer, if we update the two layers simultaneously, the analysis will be very complicated. So even for a single transformer, it is very difficult to solve. So we follow the existing literature on a single transformer analysis. So we employ a three-stage training of the MOT model. So in the first stage, we freeze the attention but update FFN only. So we want to FFN to obtain its own specialization during the first stage. And we employ the normalized gradient descent to update it. Because if we calculate the normalized gradient, the W is updated in a moderate step. So so the router can encourage the exploration across all transformers. So that's the update of stage one. Well, at the end of stage one, the FFN has developed its own specialization. So we freeze the FFN and update attention. So we want attention to align with the FFN's specialization for each transformer. So after stage two, we freeze the attention again to update FFN, or actually to fine tune FFN to further reduce the training loss. So that's the three-stage training for the transformer. But for the rotor, we keep updating theta over time. So this is the training algorithm for the whole MOT model. And based on this algorithm, next I will print our theoretical results. So first is the result of stage one, so FFN specialization. I first define the specialization here. So I let Ni star denote the index of signals for which transformer is most specialized. So here, Ni star corresponds to the task that has the maximum linear combination of W and Vn. Because if this is larger, the loss will be smaller. So that's why we select the maximum N to be the specialization of transformer by I. If we fix the task N, so its specialization X per set is Mn. So Mn contains all the tasks whose sorry, Mn contains all the experts I whose Ni star equals N. So that's the specialization set for task N. And based on this definition, we propose this proposition to show the result of stage one training. So we prove that at the end of stage one, each FFN has developed its own specialization. So there is the linear combination between W and Vn I star is obviously larger than others. So each FFN has obtained its own specialization. And for the rotor, it can always select the correct expert for each data point. So the rotor actually has converged at the end of stage one. And this is so next I will introduce the proof of this proposition, the basic idea of this proof. Actually, we make use of the conflicting examples to show the gradient. So for example, we consider two samples xk. They have the same class signal Cn, and but they have different labels. So one is positive one, so positive Vn. Another is negative Vn, minus Vn, and their noise vectors are same, but still has a different noise labels. So this sample will push. So these two samples will be rotated to the same transformer during the stage one. So this sample will push the gradient with respect to Wm to align with Cn because this label is positive one. So this gradient will be pushed to align with Cn because Cn is also positive. While this sample will push the gradient to the opposite direction. So when combining the two samples, the two gradients, we found that the gradient with respect to Wm towards Cn is almost zero. So Wm will only be sensitive to Vn. That's why we define the specialization as Vn here. Well, for the rotor, it is similarly, we can similarly use the conflicting examples to prove that theta m will only be affected by Cn. So that's why the gating can identify the correct class N for each transformer. So because the theta only will only be affected by Cn. So that's the basic idea of this specialization. And thanks to the specialization, so since stage two, each transformer will only accept data point with the same Cn. So the attention wants to identify the Vn for the FFN because Vn actually decides the correct label. So we prove that at the end of stage two, only Vn's self-attention becomes near zero, near one, while others are near zero. So the attention layer, so recall that attention layer serves as a filter, so it will only output Vn for the FFN. So Vn will be used to do the classification in FFN after stage two. And the proof is also similar by exploiting the conflicting signals such that WQQ will only be sensitive to Vn. And finally, in stage three, the FFN, we will polish the specialization of FFN. So we will want to train it to further reduce the loss. So we prove that at the end of stage 3, the linear combination of Wi and mu will be much greater than 1, such that the loss can approach it to near 0 for the MOT. So this convergence term is in an order of log epsilon power minus 1, because we can employ the strong convexity of the loss function. And also it thanks to the specialization of transformers, and it successfully avoids conflicting examples trained in a single transformer. So there is only one feature in each transformer to be trained to update W. So the acceleration, so it greatly accelerates the convergence. And finally, I will compare it with the benchmark case. So for the first, for the standard single transformer with multiple attention head, we use a conclusion developed in a very recent paper. So it proves that it also employs a three-stage training for a single transformer, but its convergence time is epsilon minus 1, power minus 1, because the conflicting samples are trained within a single transformer. So the convergence is delayed by these conflicting samples, but ours greatly accelerates this process. Where for the attention absent MOE, we prove that it cannot reduce the expected tensor error to be smaller than any epsilon because of the existence of Gaussian noise. Recall that the attention serves as a filter, so it can only output Vn, so it successfully get rid of the Gaussian noise, and it can reduce the noise to be it can reduce the error to be any small epsilon, but the attention absent MOE cannot. So finally, here's our experiment results. So we validate our theoretical result in CFAR 100 and CFAR 10 datasets. And we also conduct NLP tasks to verify our theoretical results. One interesting point is that if the, oh, yeah, okay, sure. So there are two, I will introduce two interesting points. One is that if the number of transformers is already good enough, we increase the number may not be better for the system performance, because it may require longer exploration time for the transformer. And also for the MOT, if the task is more complicated, the performance is better. So that's because the capacity of MOT is better compared to a single transformer. Okay, yeah, that's all about my presentation today.
Thank you, Hongbo, for your wonderful talks. Very interesting topic. So we still have time for one quick question. Is there any question for Hongbo? So let me ask a quick question. So in your setting, are these transformers also trainable, right?
Yes, yes. So initially the WKQ matrix are 0, so are generated by this Gaussian noise. So they
Yeah.
to be trained.
Yeah, understand. This is okay. Because I'm thinking about a pre-trained model, because when we are like using big companies pre-trained model, let's say
Yeah.
we don't have any training resource, so we only have some resource to train the scaling network. So how does your analysis or study like motivate such a analysis into such a regime? So in this case, like we can only change the gating network or router.
So you mean if we use the pre-trained model, so each transformer is we don't need to train the transformer, just to
Yeah,
train
we
the
yeah
gating.
yeah yeah.
Yeah, that could be possible, and this would be easier. But also, I think um, if if we use the pre-trained model, the performance may be not very good, because the specialization is not very clear of each transformer. So we still need the different expert to have its own specialization, such that they can handle different tasks. So so even though we use pre-trained model, we can still fine-tune each transformer in this training process. But the result, I think it should be similar.
Okay. Yeah, thank you. Thank you.
Yeah,
And
thank
let's
you.
thank Hombo again for his wonderful talk.
Okay.
Our next speaker is Yi, Yi He. And he is a PhD student in the EC department at Wayne State University. His advisor is Professor Xinyu Zhou, and previously he received a bachelor's degree in software engineering from Beijing Jiao Tong University, and his research interests are in machine learning, stochastic systems, with a focus on reinforcement learning and policy optimization. And today he's going to bring us his recent topic on policy optimization. So yeah, go ahead.
Hello, can you see my screen?
Yes.
Okay. Hi everyone. First of all, I'd like to thank Dr. Liang for the invitation. My name is Yihei, and I'm a fourth-year PhD student. Today, I want to share one of our recent papers, which has been accepted by NUPS 2025. It discusses the sample complexity of differentially private policy optimization. So before I dive into our detailed contributions, I'd like to briefly introduce some background information. So first, our work focuses on the policy optimization method. So what is policy optimization? Suppose we have a policy theta t now given a state xt. Based on this policy theta t, the system performs some action yt, and then we obtain some reward rt. Based on this reward, by using an update method, we can update the policy from theta t to theta t plus 1. That's the basic idea of policy optimization. And our objective is to maximize the following equation, which represents the expected reward. Here, x is sampled from some initial distribution rule, and y is sampled from the current policy theta. Okay, so now why do we focus on the policy optimization? Actually, policy optimization is a cornerstone of modern reinforcement learning and one of the most widely used RL methods. Unlike value-based method, policy optimization directly optimizes the policy itself, which often leads to better performance in complex environments. So some core algorithms in this area include policy gradient PG, the natural policy gradient NPG, and the trust region policy optimization TRPO, and so on. Moreover, policy optimization has a rich theoretical foundations that has been established over decades. However, while policy optimization has achieved great success, there are important privacy concerns we need to address, especially when learning from sensitive data. Let me give you two concrete examples. In healthcare RL, the state consists of patient's medical history, and the action is the treatment decision. The reward is the health outcome. The risk here is the potential leakage of private medical data. In LLM training, the input includes user prompts that may contain private information, and the process involves model training or fine tuning. The risk is that the model may memorize and later show the sensitive content from the training data. The key issues is that both cases involve optimizing over sensitive data without formal privacy guarantees. This is exactly the problem our work aims to address. To address these privacy concerns, we turn to differential privacy, which has become the golden standard for modern data protection. Proposed by Dwork et al., differential privacy formalizes privacy guarantees by ensuring that the outcome of an algorithm is nearly unaffected by the presence or absence of any individual user's data. Differential privacy has already demonstrated real-world success in several domains. It has proven successful in both supervised learning, federated learning, and also data analysis. However, when it comes to reinforcement learning, this remains an emerging frontier. Applying it to policy optimization in RL represents unique challenges that are not yet fully understood. This is exactly the gap that our work aims to address. So this brings us to the key research gap, the lack of theoretical understanding of privacy in policy optimization. Currently, we have extensive theory for policy optimization and broad development in safety critical domains like healthcare, LLM alignment. However, there are still three critical problems remains unsolved. First, there's no theoretical result exists on sample complexity under DP for policy optimization. Second, the standard differential privacy notion fail under the on-policy data generation. And third, there's no unified framework. So without a solid theory, privacy-preserving policy optimization remains empirical, limits its safe and reliable development. Our work addresses this gap. So to address the gap, our work tackles three fundamental questions for private policy optimization. First, the definition. What is the right notion of differential privacy for policy optimization? As I mentioned before, the standard DP definitions do not work very well on policy data generation, so we need to establish an appropriate privacy notion. Second, the framework question. How do we design a unified framework for private policy optimization? We need a system approach that properly integrates privacy guarantees into the policy optimization process. And third, the theory. What is the sample complexity cost induced by the differential privacy in policy optimization? Now let's dive into the first question. What is the right notion of differential privacy for policy optimization? Let me first review the standard mathematical definition of differential privacy proposed by Dwork et al. It says a random algorithm M is said to satisfy absolute delta dp if for any two dataset D and D prime that differ only one record. For any possible outputs, S would satisfy this equation. This means that the algorithm's output distribution should be nearly identical whether or not an individual's data is included. On the left, here is an example of the healthcare. On the left, we have John, one of the patients whose data is sent to the hospital to train a model. When John's data is included, the model learns that for patients like him, the hospital should choose medicine B about 70% of the time and medicine A about 30%. But there is also an attacker, Ethan, who already knows almost everything about the population and can see the model's outputs. The only thing she doesn't know is was John's data used or not. Now look at the bottom. If John is not in the training data, the model's output changed to 60% for medicine B and 40% for medicine A. So the difference tells Ethan, since the model shifted, John must have been in the data. So even though we didn't publish John's record, his participation can still be inferred. This is exactly the kind of leakage that happens without differential privacy. In this case, with DP, we will add some noise, such like Gaussian noise, to the system, and our goal is to make the model's outputs look almost the same, whether John is in the training dataset or not. In this case, we can see the difference between training with John and without John is quite small, and then Ethan cannot have a high probability to infer whether John is in the dataset and then infer more information. Let's go back to the mathematical definition. There is still a question we need to address. What constitutes a one record? To answer this question, we need to understand the different granularity of differential privacy. Let's consider item level DP, which is a classical setting. In item level DP, two datasets are considered neighbors if they differ in exactly one interaction record, as shown in the picture, where one record is highlighted in orange. In supervised learning problem, the standard item level DP notion can be directly applied. As shown in this example with mixed digits, we have two datasets where the data points are IID. The dataset differ by only one record. In this case, one image changes from digit 4 to the digit 3. Since the data points are IID, item level DP works perfect in these settings. The presence or absence of a single training example has a bounded impact on the model. However, we will see next, this assumption breaks down in policy optimization. So why doesn't previous notion cannot work in the policy optimization? One issue is that there is no such fixed data set in policy optimization. Unlike supervised learning, where we have a pre-collected data set with features and labels, as shown here, we have both feature X and label Y. However, policy optimization is fundamentally different. We sample X from some distribution and then by our current policy theta, we generate an action Y and then we can obtain the reward. This creates a dependency structure where each data point depends on the previous policy updates. More importantly, the neighboring relationship of differing in one sample xi yi actually does not hold in policy optimization. Let me illustrate this with a question. Look at the picture. Can this really be true if we have two data sets where only one sample differs, say x2, y2 changes it to x2 prime, y2 prime, as shown by the red box? Can all the subsequent samples remain identical? The answer is no. When we change one sample x2, y2 to x2 prime, y2 prime, this leads to a differential privacy update. Consequently, all future samples will be different because they are generated from this updated policy. As you can see, the third and fourth samples x3, y3, and x4, y4 also change. This cascading effect means that changing a single sample can affect the entire trajectory of subsequent data collection. This fundamental property of on-policy learning breaks the neighboring relationship of item level DP, which is why we need a different policy notion for policy optimization. This leads us to our proposed definition, DP in PO. It says we consider a policy optimization algorithm M interacting with a set of n users, and MD being the final output policy. We say if this algorithm is satisfies the DP, it should, for any two dataset D and D prime differ only by one user, it will satisfy this equation. So the key insight here is what means a user. For example, in large language model, each user can be each prompt X. However, the response Y and the reward RXY are dynamic since they are determined in an on-policy manner as the policy evolves. This is in sharp constraint to supervised learning, where the entire dataset is static and fixed in advance. Now let's move to the second question. How do we design a unified framework for policy optimization? To answer this question, we proposed a meta-algorithm for private policy optimization, which consists of three main phrases. First, the sampling phrase. For each iteration, we collected a fresh data set. We collect a fresh data set of size M using the current policy pi theta t and the reference policy mu. And second, the evaluation phrase, we estimate the advantage function a pi theta t using the advantage estimator hat a hat, which is computed as the reward difference. And third, the updating phrase, we call a private update oracle on the data set dt to find the next policy theta t plus 1 while maintaining differential privacy. This meta framework is general enough to apply various policy optimization algorithms by specific different kind of private update oracles. The key theoretical result that makes this framework work is proposition 1, which provides the privacy guarantees for our meta algorithm. This is a powerful result because it shows that if we can design a private update oracle that satisfies the standard DP for the updating phrase, then the entire meta algorithm automatically satisfies the DP in PO. This result simply follows from our one-pass algorithm and adapt to parallel composition of DP by noting that changing one user will only change one record in DT over a single T. And our framework can also extend to online settings and even joint differential privacy by using the so-called billboard lemma. Now let me show you a concrete instance of our framework, differentially private policy gradient. On the left, we have the vanilla policy gradient algorithm, which is one of the simplest and the most direct approaches. The update rule is theta t plus 1 equal to theta t plus eta times the gradient, which can be seen as the gradient ascent. By the classical policy gradient theorem, the gradient can be written as follows. On the right, recall our meta algorithm. We can show our algorithm 2, differential private policy gradient, which follows from our meta framework. What we only need to change is to determine what is the specific private update oracle here. For DPPG, the private update consists of 3 steps. First, we compute the gradient and then add some Gaussian noise to get the private gradient. And third, use the private gradient to update the policy. Another approach of our framework is DPNPG. The natural policy gradient use the feature information metrics to improve the update direction. The update rule is shown as this equation. However, in practical, we usually use an equivalent way to write the update rule as follows, where the WT is the solution to the optimization problem as follows. This formulation essentially reduces our policy optimization to a sequence of regression problems. On the right, like before, we recall our algorithm 1 and apply the private update oracle such like this. We will call a private LS oracle to find an approximate minimizer WT of this equation to solve such a regression problem. And we also accommodate a differential private rebel, which stands for regression to relative reward-based RL, which is very similar to MPG. Both of them change the update to a regression problem. So we will only show some results of the MPG since they are quite same. Now let's address the third and the final question. What is the sample complexity cost induced by the DP in policy optimization? For the theorem 1, it shows that if we can properly set the Gaussian noise in algorithm 2, which is DPPG, ensure that the algorithm would satisfy the epsilon delta DP. And based on such LS assumptions, we can derive our FOSP convergence. And for this first order stationary part convergence, here has a interesting balance for a fixed n. The key here is to balance between the bench size m and the number of updates. As so balance between the per iteration accuracy and the total number of updates. This balance depends on the specific choice of private update oracle, like DPPG, DPNPG, and DP rebel. For the if we have LS assumptions and such feature non-degenerate assumption, and also a very common compatible, we can derive this lemma 1. And we can see that this lemma has one term matches the FOSP's result. So just apply the FOSP here, and we can derive our theorem 3, which is a global optimal convergence. And we can see for the first term, it is matches the non-private case. For the DPNPG, so to start with, we should assume that the approximate minimum WT returned by the private LS should satisfy this assumption. The least square oracle should bounded by some LT square here. And note that this assumption is algorithm free, means that one can insert any private regression as long as he can provide this sample error bound. And we also need some assumption 4, which is also very standard, which allow us to use some telescope sum to get some standard results. By these two assumptions, we can derive our theorem 4, which is a master theorem. We can see here still have some a term LT to bounded. So to derive this LT, we should refer to our assumption 3, and originally it comes from the private LS oracle. So we only need to determine the estimation error under different types of private LS. Here we have two approaches. For the first, we can use such exponential mechanism by sample WT with the following distribution. We can derive the lemma 2, and after apply this lemma 2 to our previous master theorem, we can have our first general function convergence here. And we can also see that it is still have two terms, and the first term, the sample complexity of the first term also matches the non-private case, and the following term contains a privacy parameter would perform as a lower term. And we can also consider this approach if the policy is log linear and the reward R is reliable. Our assumption 3 will reduce to the estimate error of the linear regression. Then we can apply different kind of algorithms. Here we choose ISSP in Brown et al. Then applying the result of this paper, we can have the bound M should larger than this kind of bound, and apply this M to our master theorem. We can have our global optimal bound here. However, one can directly replace this algorithm with more efficient algorithm if there are if it is available. However, for the high dimension, we cannot use such ISSP algorithm. Instead, we induce the Qin et al.'s paper and have this kind of bound. And we see the sample complexity bound is also a non-private term plus a private term. And the private term also perform as a lower term of the sample complexity bound. So here are some conclusion. For the definition, when we define our DP impure instead of previous traditional DP, and for framework, we reference a meta-algorithm for private pure, which builds up upon different algorithms like DP, MPG, Rebel, and maybe other policy optimization methods. And for the theory, we demonstrate that the privacy cost can often perform as lower term in the total sample complexity. And here are some reference.
Thank you, Yi, for your wonderful talk. It's very interesting. You can still use the differential privacy in this policy optimization. So let's first to open the floor to the audience. Is there any question for Yi for his talk?
Sorry, let me share it.
I have a quick question for the for your definition for the differential policy, differential privacy definition.
Okay.
So yeah, it's very interesting. You can extend this to the background of this policy optimization. So I understand your point in that in supervised learning, the data sets are usually fixed. So here we assume the X are fixed. But so here you say you are fixing the users. No, you try to model this definition by differing one user. So my question is that shouldn't this which user to choose to be also random in at each step? Because I understand is that you 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 update your model and you randomly choose some users and then you evaluate the advantage function on these users, right?
Yes.
So
In our current framework, we assume one round interaction per user. Yeah. What's your point?
so I'm just trying to understand whether these users are fixed or random.
Yeah. The users should be fixed in advance. Like previously we have X. For the supervised learning, we have both X and Y. But for here, we should fix our X and just leave the Y to be sampled from our current policy. But the user means X should be fixed in advance. Yeah.
Okay.
Sorry, I can't hear. Like the users can also be random. Like you can fix a set of users, but
Yeah.
those users are sampled from the distribution, so they are equivalent, right?
Oh, yeah.
It doesn't matter whether it is a random or fixed, because because we are doing one pass, so you can get your fixed data set by a random sample n times, right? And each time you work with a new user, that is equivalent to sample from a distribution. So they are equivalent.
Okay.
Yeah, does that solve your question? Like, there is no difference. So I think the only requirement here is that we just allow one user contributes to one round. That's it. Yeah. Think about it like one pass SGD, right? That's the same. Yeah.
Yeah, because in SGD, your data you can is also still your X are given, right?
Yeah, but your SGD, your X is given in advance, right?
So in RL, your X is chosen by your current model.
Oh no, X here is a state, right? Prompt that is not chosen by
Okay,
your
oh,
model,
that's
right?
the prompt. Okay, I see.
X is
Yeah.
the prompt, and Y is the response. Yeah.
Okay, got it. Okay. Yeah, thank you for clarification.
Sure.
Any other questions? So if no, let's thank our speakers again for today's wonderful talk. And thank you all for joining today.